Hello everyone. Today I would like to take you through my AI project called the Reason Parser, as everyone can see, and by names of Moses. I have very many names, but I choose to use those ones, official ones. So, uh, Makerere University, that's my college where I study from. So today I would like to take you through a Reason Parser and the dataset we are supposed to use. By the way, for those who don't know what a reason passer is, this AI project is to help out a real life problem whereby very many companies uh, advertise their jobs and usually find that the applicants are they are over 100 plus, and it's so difficult to find time or create time to go through all those applications one by one at a time and find. Okay, it's really tiresome, as you can imagine. So the resume passer, it's an AI project which can help us go through all those those applications, and it does it instantly, and it will tell you the eligible applicants for that particular job. But of course, we are going to need data before we reach there, of before we reach that point of of the program, or let me say of the whatever it is, to sense. So we have to create an algorithm, I may call it. It's an algorithm whereby we have to feed it with data, and AI is all about data, and we are supposed to choose a particular data set. Like, what are we going to use? What are we going to feed into the machine or our algorithm to get used to those things? It has to cope up and get used to it and make it think of the possibilities which can happen. So by that, it will help us to go through all those applications at once. It will save our time, save money, get and even tribalism at some point. Yeah, and the cause for it, it will choose by merit, not by or tribe or what, because some people usually look at what they know, but this one, it will be by merit. So it will try to solve all those problems, and this is the 21st century, so things are becoming so technological, and Reason Passer is one of the AI project I choose to work on. So as you can see, for those who doesn't, a dataset is simply a collection of various types of data stored in a digital format. Data is the key component of any machine learning project. Yeah, so for those, if you want to get in dataset, there are very many links, but I choose Cargo as my source of my information. That's where I'm going to get my dataset. Actually, I've already got it. I'll be putting a link on this YouTube down there below. You can click on it and you see my dataset. Sorry, it's on my drive. So what are the considerations you're going to take when you're choosing a particular dataset? Yet your dataset has to be accurate, it has to be consistent, and timeliness, and its size also matters. By accuracy, I mean that the information you're getting is correct, you've got it from the right sources, and consistency, it has no contradictions. Like, maybe let me say that data, maybe, like for my case, I can't say that the keyword for the maybe for the data science applicant, there must be that it must have this a certain certificate. Again, another one, I say it must not have that certificate somewhere. So it brings a long contradiction. So you're going to be confusing your algorithm with inconsistent data. Yeah, so the data has to be consistent, Timeliness means that the information or the data is up to date. You know, things advance, like things continue upgrading. So you may find that maybe in 1999 they just required a degree for one to do a particular job, just a degree. And for now, there are other certificates one must add on in this 21st century for them to help out. As data increases, also the weight of the job you're going to do, you must be having some good knowledge about it. So the data size also matters. Most of the time in the algorithms we make or the projects, you may find that if the data size is not big enough or it is imbalanced, by imbalanced I mean that it falls more on the positive side than the negative side, or either way. So you may find that you may not get the right thing you want from from your algorithm. It won't give you the right expectations. As a bonus, I want to take you through, there are some theorems, like if you want to know to bit by it around this AI project. There are these theorems, like as you know, mathematics is everywhere, it's a wide thing. So there is what they call bayesian theorem. It is simply a mathematical formula for determining conditional probabilities, dependent factors, whereby I mean that it's dependent to a condition that if you have something, maybe something can't happen before the other one happens. Let me say maybe the ground can't get wet before it happens. So the wetness of the ground depends on the rain which comes. So as you can see, that's it, that A, probability of A given that B. So A happens given that B has already happened. That's what they call Bayesian theorem. And the probability of A occurring, probability of B occurring, that's it. So I came and explain further considering what I've just said. But there is what they call Bayesian theorem. Simply, it's about dependence of the two subject matters or the predictors. We may say that maybe in my project, that if someone has this degree, must also have this, you get, must have this kind of qualification. If someone has a degree, doesn't need to have a certificate. So it's about depending. So there's what they also call naive Bayes theorem. This is an advance of Bayes theorem. Leaving Bayes theorem alone, this is naive, that there are some factors which are not going to directly depend on other factors to happen, you get, but they are there to happen, you get. No matter, it is one of it to happen, but it is not necessarily the fact that if it happens, the other one also happened. No, it doesn't actually really depend so much. That's why they call them naive. Sometimes they just happen. They are so naive, and for that it actually comes from the Bayes theorem itself, that probability of B to happen is equal to probability of A intersection B, of A, and we can say multiplication factor. By that we can say that A intersection B is equal to probability of A to happen given that B times of the probability of B to happen given that A has happened. So here you can see that when you're getting the probability of A given that B, it is simply, you just substitute the other one. They call it multiplying factor. Considering, now I give an example, considering the predictors below A and B and C. You're going to find out that B, like A, it doesn't have a depending factor, but B to happen has to depend on A, and C depends on A, B, C, but it's not how it is. You're going to find that C will happen no matter what, A does not happen as long as B is there. So C is always independent of A, and that's naive. And in this case, the predictors are considered to be independent in the case that any of the two conditions can be used to predict the future decision. So you can either use A and B to give the final decision, or B and C to use the final decision. It is not the matter of the case that C to happen, it must depend on A and B must have happened. No, that's why they are called independent factors. They are not. They don't follow the whole chain of what, of the dependency. So they are a bit independent, and after that there is what they call the Bayes network. Yeah, Bayes network. For it tells you when, it helps us to know, it gives us knowledge to know when when is it supposed to be dependency, when is it supposed to be when is it supposed to be dependency, and when is there supposed to be independency. Yeah, there are some cases that maybe for example, that from here I say it's an ideal for taking an event that occurred and predicting the likelihood that any one of several possible known causes was the contributing factor. And for example, here I took for the disease and the symptoms. Now, if someone is vomiting, you may consider that person. You may assume, because you don't know yet, you may assume that maybe that person has malaria. If the person has fever, you may assume that the person has malaria. So, and in most cases, the doctors, if you have fever or malaria, they will actually ask you, are you vomiting? So, and it's not that when you vomit you have fever. So it's just like a circle. Yes, not whenever you vomit you're sick. It's not, but it's one of the chain. But when are you supposed to know that malaria is actually fever? Malaria is the one actually causing the fever. You get? So someone has malaria, so must have fever. What is causing the malaria? It is fever and vomiting. Yeah, but is it true? Not always. And that's what Bayes tells us. You may find that now in this case, you can see that vomiting and fever, malaria to have malaria, you must be vomiting and fever. Right? Yeah, and it performs a parabolic forms a parabolic continuity. For those who may want to know more about these laws, I'll provide the link below on my YouTube channel. You'll be able to go there and actually read about more of it. So here I came and I said naive versus Bayes. We want to find out what's the difference between naive Bayes and Bayesian theorems. The main distinction between Bayesian theorem and naive Bayes is that naive Bayes assumes that all factors are independent. You can either use either of the two to do what, to predict the outcome, or you can use that's it actually. Then Bayesian theorem, they are dependent. For it to happen, the other one must have happened. It is a must for it to happen. Like there is no way maybe someone can do what? Can walk without making steps. So it is so depending that for you to walk from one place to another, you have to make some strides. So it's really dependent. The other one is independent. The other one is dependent. Bayesian theorem is dependent. And for the fact that Bayesian networks are naive Bayes, for them the conditions, naive Bayes assume that conditional dependency. Take persist, for instance, x given that y and z is equal to xz. Yeah, so it does not necessarily mean that x will always depend on x and y, z and y. Get here, x given y z is the same as x